if you talk about the erythropoiesis, 3 points, 3 headings under which the steps in erythropoiesis should be described: the cell size, the nucleus, and the cytoplasm. Let's try to understand this. Cell size. Look, the most precursor cell, pluripotent stem cell, is 24 microns diameter, but matured RBC is only 8 microns diameter. So, the cell size goes on decreasing in the subsequent stages or subsequent steps. With each step, the cell size will reduce. And why is that? That is because of a very rapid cell division. So, to put it simply, if this is a parent cell, it divides into 2 daughter cells. Now, before the daughter cells could regrow to the or grow to the parent cell size, they are divided further, which means with subsequent steps the cell size will go on decreasing. Okay, so remember, this is the first of the 3 points that you should remember. Cell size goes on decreasing during the erythropoiesis with each successive step. And second, nucleus. Look, the most precursor cell, pluripotent hematopoietic stem cell, is nucleated, and up to the late normoblast stage, the cell has nucleus. But beyond that stage, the nucleus is extruded out. So, through subsequent steps, what you must remember is that initially the nucleus is occupying an important space in the cell, in the precursors of erythrocytes, and slowly through subsequent steps, the nucleus will become smaller and smaller and smaller. It will go to the periphery, it will be pushed to the periphery, and finally in the late normoblast stage, it will become a pycnotic or very small nucleus. Finally, it will get fragmented and it will be thrown out of the cell. So, remember, blast is an immature precursor of the RBC, and up to late normoblast stage there is nucleus, and beyond that stage there is no nucleus in the RBC. So, nucleus is the second change in the erythropoiesis. And the third one is cytoplasmic changes. Cytoplasm goes on changing. Look, initially the RBC does not have hemoglobin, but eventually the hemoglobin is going to appear. Remember this, RBCs, their main function is to carry oxygen, and that's by hemoglobin. So, initial stages are basophilic, because look, basophilic, phil is to love or attract. They attract basic stain, they attract basic dye. That means the content in the initial stages, the content is acidic, so it attracts basic stain, and that's why the cytoplasm is basophilic. But in the intermediate normoblast stage, hemoglobin begins to appear in the RBCs. Now, hemoglobin itself is basic in nature. So, from this stage onward, it will start attracting acidic stain and will become acidophilic. So, the point that I am saying is cytoplasm initially basophilic, and once the hemoglobin starts appearing, it becomes acidophilic. So, 3 steps, remember: cell size during erythropoiesis, what happens to the nucleus, and then what happens to the cytoplasm. RBC count in males versus females. Very often the students tend to say that the females have a lower RBC count because of the menstrual blood loss, menstruation in females. Well, that's not entirely accurate, because our body is based on negative feedback mechanisms. whatever change happens in the body tries to do the opposite and rectify that change. So if the blood is let out of the body, then the body's bone marrow will start producing blood or start producing the cells. So the average blood loss during menstruation every month, about 20-30 ml, that would not cause less of RBC count in females. Then why is it that the RBC count is less in females? Let's say it's not less in females, it's more in the males. And why is that? Because males have the androgens, the testosterone, and testosterone stimulates erythropoiesis. So please remember, in the vivas, if you are asked why the RBC count is less in females, it's not less in females, rather comparatively it is greater in number in males, because testosterone stimulates erythropoiesis. There is evidence that testosterone stimulates erythropoiesis in 3 ways. One, it goes to the kidney and causes release of erythropoietin, the hormone that stimulates erythropoiesis. 2, it goes to the bone marrow and upregulates the erythropoietin receptors in the bone marrow. So erythropoietin will act on the bone marrow and erythropoiesis will be stimulated or hastened. It will be made faster. And 3, in some unknown way, testosterone directly stimulates the rate of erythropoiesis. Therefore, the reason that males have higher RBC count is the testosterone. Estrogen has been shown to, there is some evidence that estrogen may suppress erythropoiesis, and therefore females may have a lower RBC count, but there is no conclusive evidence to prove this. Therefore, males have a higher count compared to females. That's the correct statement, and that's because of the presence of testosterone. Vitamin B12 deficiency, megaloblastic anemia and pernicious anemia. Very often the students confuse the term megaloblastic anemia and pernicious anemia. There are a few things which are common in that, so one must understand. Well, vitamin B12 deficiency results in these 2 conditions, the megaloblastic and pernicious anemia. So, look, first of all, what are the reasons for vitamin B12 deficiency? First, if it is deficient in the diet, then it will lead to vitamin B12 deficiency. And let me add here, vitamin B12 deficiency does not occur that easily. I mean, it takes months or years of the deficient diet that will result in vitamin B12 deficiency. But nevertheless, dietary deficiency can lead to vitamin B12 deficiency. Second, if stomach is not able to release intrinsic factor of Castle, remember B12 combines with this in the stomach, and this combination goes all the way to the ileum from where B12 is absorbed. So if for some reason intrinsic factor of Castle is not secreted by the stomach, then B12 deficiency. And third, surgical resection of ileum. If the ileum has been surgically removed, then vitamin B12 cannot be absorbed. Remember, vitamin B12 has to travel all the way through the small intestine to reach the terminal ileum from where B12 is absorbed, and it's the job of intrinsic factor of Castle to combine with B12 and take it safely to the ileum and then absorb from the ileum. So surgically, if the ileum is removed, B12 deficiency will occur. Why does it result in megaloblastic anemia? Look, first of all, blast is immature precursor and mega is large. So remember, vitamin B12 and folic acid, these two are required for nuclear maturation. And you know, RBC precursors are nucleated. So if there is a deficiency of B12, then nuclear maturation DNA synthesis and nuclear maturation would not happen, and therefore the cell division will be slowed down. The cell division will be hampered through the successive stages of erythropoiesis, successive steps of erythropoiesis. And if the cell division has slowed down, then the subsequent steps, the cells will remain large and immature because nuclear maturation has not happened. So, this will result in the megaloblastic anemia. It's a blurred picture. It's a peripheral blood picture. If you see the peripheral blood smear, there are large immature RBCs. Then what is pernicious anemia? Pernicious is very grave or dangerous. One reason for that is chronic atrophic gastritis. I mean, imagine that the stomach lining has been completely destroyed. What will be the result? Intrinsic factor of Castle and other secretions of the stomach, all of them will be absent. Now what happens is there will be absolute deficiency, absolute lack of B12, and what the B12 will be required for even Schwann cell proliferation, nuclear synthesis in all those cells which are proliferating. And therefore what happens is Schwann cells, which are going to cause myelin formation for the nerves, the Schwann cells cannot proliferate, and therefore the resultant condition is the neuropathy. Particularly in the spinal cord, there would be degeneration of the nerves, and peripheral nerves also show degenerative changes. So pernicious anemia, what is pernicious? Because it shows neurological manifestations, it is called pernicious anemia. So remember, pernicious anemia generally results from an autoimmune origin. Autoimmune, where antibodies are developed against the parietal cell that synthesizes and secretes intrinsic factor of Castle. So absolute lack of this factor, therefore absolute lack of vitamin B12, and therefore the neurological manifestations, because the cells which cause the myelin sheath for the nerves, those cells cannot proliferate, the nerves degenerate, particularly the manifestations of degeneration of nerves in the spinal cord. So that's pernicious, very grave, very bad. And in pernicious anemia, the peripheral blood picture will be that of megaloblastic anemia. The RBC picture will be that of megaloblasts. So remember the difference in these two terms, megaloblastic and pernicious. The common thread is vitamin B12 deficiency.